Hello and welcome back to the Deep Dive. Today we're tackling a name you definitely know, Thomas Edison, but maybe not in the way you think. We're looking past just the light bulb inventor myth. Our deep dive today presents him as something much bigger, the architect of motion infrastructure.
That's right. It's a really interesting perspective from our sources. Most people think inventions, right? Gadgets. But the core idea here is that Edison fundamentally made motion, electrical motion, sound motion, into, well, a business, a habit, and a citywide utility.
Okay.
So our mission really is to unpack how he managed to take all this chaotic, unpredictable energy and motion and engineer it.
Yeah.
Engineer it into the stable, predictable loops that, honestly, our whole modern world runs on. We're using this framework called motion theory to explore that.
Motion theory. Okay, that's definitely a new angle for a lot of us, myself included. So when you say motion theory, what does that actually mean in practice? How does it change how we see Edison?
Yeah, great question. It's less about, hardcore physics equations and more about a mindset. Motion theory, in this context, is about seeing how Edison viewed processes. Electricity, light, sound, even moving images, he saw them as dynamic flows, as motion.
Not static things.
Exactly, not static things. And his real genius, the theory argues, was figuring out how to tame that wild, often unreliable motion, how to channel it into these predictable, stable loops, complete with guardrails to keep things safe and consistent. His aim wasn't just a one-off invention. It was about creating a service, something so reliable, so repeatable, you just forget it's even there.
Right, which ties into that famous question he supposedly asked, a very practical, almost civilization-level question. How do you make electricity boring?
Boring meaning dependable.
Dependable, safe, metered, everywhere. So it just blends into the background. So this deep dive is really about unpacking how he achieved that massive goal by mastering these motion loops. Okay, so when we think about Edison's approach, it's important to realize he wasn't maybe the pure theorist in a lab coat or the super elegant engineer creating perfect single objects. Our sources really paint him as more of a systems composer. Is that fair? Taking these rough, experimental electrical rhythms and orchestrating them.
That's a perfect way to put it. Systems composer. He took that raw, chaotic motion and turned it into what we now see as smooth, reliable services. And the motion theory lens helps us see the how. It boils down to designing these stable loops with built-in guardrails. Think of it like channeling a wild river.
Into canals and irrigation.
Exactly. He engineered specific kinds of loops. You've got the source loop, the generators making the power, then the carrier loop, that's the wires getting it places, and the load loops, the light bulbs, the motors, the things actually using the power. But, and this is critical, he didn't stop there. He added protection loops, things like fuses, circuit breakers eventually to prevent disasters, measurement loops, meters so you could actually bill for it, make it a business, and maybe most importantly, governance loops, the standards, the safety codes, the rules of the road for electricity.
Wow.
So if you zoom out, a modern city, electrically speaking, is basically just this vast network of synchronized motion loops. And Edison, he effectively built the first working prototype for that entire system. He laid down the infrastructure, the invisible plumbing of modern life.
Yeah, that's a much bigger picture. And he built these prototypes, these early motion machines in his famous labs, right? Menlo Park, later West Orange. The sources describe them not just as invention factories, but as the first industrial R&D feedback machine. What does that mean?
It means they were designed for what we'd now call closed-loop innovation. The lab itself wasn't just a place, it was a process. An oscillator, as one source put it.
An oscillator? How so?
Well, think of the cycle. An idea pops up, it gets prototyped fast, then it gets tested, maybe even pushed into the market quickly. And then, this is key, the feedback comes flooding back. What worked? What broke? How did users react? And that feedback immediately fuels the next iteration. It was relentless. Iterate, test, measure, record everything, refine. 247 sometimes, hundreds of people, thousands of experiments.
Wow, nonstop.
Nonstop, until the product, whatever it was, stabilized into a standard, until it was reliable, predictable, manufacturable, ready for the masses. He didn't just invent, he industrialized the process of perfecting inventions.
Okay, so if he's orchestrating these motion loops and perfecting them in these R&D oscillators, how does this lens change how we see his big hits? Let's start with the obvious one. The light bulb. Everyone thinks flash of genius, right? But it was more like a marathon of looping.
Absolutely. Thousands of trials. The goal wasn't just make light. It was achieving a stable thermal-radiative loop, making light that lasted.
Stability. That was the key.
Stability was everything. The bulb's success wasn't just brightness. It was loop stability. Could it run for hours, hundreds of hours, without failing? Through the motion theory lens, you see every component designed for this. The filament wasn't just any wire. It had to perfectly convert electrical motion into stable, radiant motion light without burning itself out immediately.
Right.
The vacuum inside. That prevented chemical desync oxidation, which would kill the filament fast. Even the shape of the bulb managed heat and light flow. And the screw base, the socket, that's a standardized interface. A universal docking port so any household loop could safely accept the lamp. It was system design, start to finish.
That makes sense.
Yeah.
He wasn't just selling a bulb, he was selling reliable, continuous light for your home loop. While he was working on making those lamps last, he noticed something strange, something he didn't fully capitalize on himself, but turned out to be huge. The Edison Effect.
Ah, yes. That's a fantastic side story, and it really shows the power of observing these subtle motion patterns. He saw that inside his vacuum bulbs, current could flow, but only one way from the hot filament to a separate metal plate he'd put inside, like a little electrical check valve.
Huh. He noted it down but didn't run with it.
Not commercially, no,
Mhm.
but its significance, looking back through our motion lens, is immense.
Yeah.
That observation, that became the principle of the diode, the first electronic gating element.
Gate.
Yeah, think of it like a one-way gate for electrical current, or a phase check valve, maybe. It lets the motion, the electron flow, go with the intended direction, the sync gradient, but blocks it from flowing backward. This ability is fundamental. Converting AC to DC, protecting circuits.
Yeah.
It's the bedrock for vacuum tubes, transistors, basically all of modern electronics. He stumbled onto the key to controlling electronic motion.
Wow. Okay, so he's got the bulb loop perfected, and he scales up, right? Pearl Street Station in 1882. How did that take this motion as a utility idea citywide?
Pearl Street is where it gets really ambitious, you have to picture it. Lower Manhattan, 1882. Gaslight, maybe some arc lamps. Electricity's still kind of dangerous, exotic. And Edison builds this station. It's basically the first city-scale synchronization fabric. It's the moment electricity stops being a novelty and starts becoming infrastructure.
Boring utility.
The boring utility. His system was low voltage DC. Now, DC had limitations, but it was chosen deliberately. It was safer for homes back then, fewer shocks, easier to meter accurately. He built these local generation islands, keeping the distribution distances short because DC lost power quickly over distance. Fuses were everywhere, distribution boards. Safety was designed in from the start.
So it wasn't perfect technology maybe, but it was a perfect system prototype.
Exactly. Even though DC couldn't travel far, Edison wrote the essential grammar for the whole electrical grid operating system. Generation distribution protection metering service. That blueprint, that's his legacy, even more than DC itself.
Which, of course, brings us to the famous war of currents. Edison's DC versus Tesla and Westinghouse pushing AC. AC won out in the end, we know that.
Yeah.
But even with Edison's, let's say, very aggressive PR tactics against AC, how does his contribution hold up when viewed through this motion lens?
It's a fascinating clash. AC's big advantage from the motion theory viewpoint was its ability to change scale. That's the key. Using transformers, which work on AC's changing phase geometry, you could step the voltage way up to send power hundreds of miles with low loss, then step it safely back down for use in homes and factories.
Something DC just couldn't do.
Right. DC was brilliant for robust local sync islands, like Pearl Strait lighting up a square mile of Manhattan, very stable, very controllable locally. But it had poor long-distance phase economy. You couldn't build a national grid with it easily. So AC enabled that continental coherence. But while Edison fought AC hard, sometimes unfairly, we can't forget he was the one who first proved electricity could be tamed, that it could be reliable civil infrastructure. Tesla and Westinghouse scaled it, but Edison domesticated it first.
Okay, let's switch gears slightly. Edison's personal favorite invention, apparently. The phonograph. Capturing sound. How does motion theory explain that one?
Ah, the phonograph. It's beautiful from a motion perspective. Think about sound. It's not just noise, right? It's a complex motion structure rippling through the air. Vibrations?
Patterns in the air.
Exactly, patterns. And what the phonograph did, essentially, was geometry encoding. It physically carved the shape of that sound motion into the groove of a wax cylinder or disc, and playback. That was mechanical phase reconstruction. The needle follows the groove, retracing that stored motion pattern, vibrating the diaphragm, and recreating the original sound waves.
Wow. So it literally stored the motion.
It was the very first consumer device capable of storing and retrieving a specific complex motion pattern on demand. Think about that. It's the conceptual ancestor of every MP3, every streaming service, every digital sample. It taught us how to give motion a memory.
And he did something similar with vision, didn't he? The kinetograph camera, the kinetoscope viewer, moving pictures.
Yes. Another brilliant application of motion control, this one is all about temporal quantization, taking smooth, continuous reality motion happening over time and chopping it up
Into frames.
into discrete frames, yeah. Individual snapshots taken really quickly. Edison's team figured out the magic number, how many frames per second you needed to capture and display. The trick was to stay above the eye's sync threshold. Your brain has its own visual loop that processes motion. If the frames come fast enough, your brain smooths it out, stitches them back together, and you perceive fluid movement. Too slow, and it looks jerky.
Like a flip book.
Exactly like a flipbook, but automated and projected. He was basically engineering the interface between captured motion and human perception, fooling the loop, in a way.
This brings us back to something you mentioned earlier, standardization. This seems like Edison's less flashy, but maybe more impactful, boring genius. Batteries, sockets, voltages, codes, billing.
Absolutely crucial. If the inventions are the flashy actors on stage, standardization is the stage itself, the script, the backstage crew making sure everything works together seamlessly. In motion theory terms, standards are synchronization contracts. They are the agreements that guarantee different loops can connect safely and reliably.
Like a universal plug.
Like a universal plug, but for everything. A light bulb fits any standard socket. Your house wiring meets safety codes. The power company bills you based on a standard meter reading. These contracts allow millions of independent electrical devices and systems to interact predictably without chaos. You could argue modern technological civilization runs more on these agreed-upon standards than on any single invention.
So this really dismantles the myth of Edison as the lone genius inventor tinkering away in isolation.
Completely. His genius wasn't just eureka moments, it was integration and iteration at scale. He wasn't necessarily the deepest scientist discovering fundamental laws. He was the master orchestrator who industrialized the process of innovation. He built systems for feedback, created the habit of constant measurable progress, and focused relentlessly on making technology reliable enough to become invisible. That's the real triumph.
And you can trace lines directly from his work to today, can't you? These modern echoes.
Oh, absolutely. Think about smart grids. What are they? They're basically Pearl Street Station 2.0, but with digital communications, sensors, AI sophisticated telemetry managing those energy loops much more dynamically, or edge storage using batteries or other tech right in your homes or businesses to act as phase buffers, smoothing out the variable output from solar or wind, just like Edison used batteries for backup and stability.
And we still fight standards wars, don't we? USB-C, Wi-Fi versions.
Exactly. Those are today's battles over synchronization contracts, trying to get everyone to agree on how our digital loops connect. Even massive data centers, in a way, follow his utility model. They provide information, motion, data processing, and storage as a reliable, metered service, much like he did with electrical motion. The philosophy is remarkably similar, and looking ahead, motion theory isn't just about understanding Edison. It actually points towards future possibilities. Building on his foundation, we're exploring things like phase-aware grids that don't just manage energy flow, but actively manage electrical coherence to prevent blackouts or oscillations, making the grid even more stable.
Okay.
Or the idea of resonant neighborhoods, designing local microgrids, maybe for a block or a campus, as finely tuned loop ensembles that can share energy among themselves super efficiently with minimal loss, almost like tuning forks.
Interesting.
And even beyond energy or media, what about motion memory for robotics? Standardizing complex motion patterns, how a robot arm moves, how a surgical tool operates, so they can be easily recorded, shared, replayed, using Edison-like standard interfaces.
So capturing and replaying complex actions.
Precisely. And these aren't just sci-fi dreams. They come with potential engineering tests, falsifiable hooks, as the sources say. Could we build a grid phase therapy device? Could we benchmark standardized motion memory for robots? It extends his core ideas.
So wrapping this up, the final verdict on Edison. It's not just the bulb, the phonograph, the sheer number of patents. It's that fundamental, almost stubborn insistence that motion, this powerful, chaotic force, can be packaged, standardized, billed, and forgotten. He turned electricity from a marvel into a mundane, essential civil habit.
That's beautifully put. There's a great analogy one source used. If Faraday lit the spark, Maxwell wrote the score, and Tesla conducted the orchestra. Edison built the concert hall, sold the tickets, printed the program, and kept the lights on. He built the whole infrastructure, the synchronization culture that allowed the performance to happen reliably night after night.
He made the magic boringly reliable. Which leads us to our final provocative thought for you, our listener. Think about this. The highest compliment you can pay to an infrastructure engineer, like Edison in many ways, is that their work becomes invisible, so reliable, you only notice it when it breaks. So what other invisible systems are humming along in your daily life? Transportation networks, data protocols, water systems that are so perfectly engineered you forget they exist. And what does their hidden reliability tell you about the underlying motion loops that make them work? Something to ponder. We'll see you next time on The Deep Dive.